Hello everyone and welcome back to yet another summary video. In this video today I will be talking about signal propagation and channel models. My name is Muhamad Reyhan Savero and let's just jump right into it. So in terms of mathematical models, I shall describe how the signal propagates. Modulation is a component of a telecommunication system. Modulation is often used to modulate binary information. The modulation's output is an analog signal. The analog is in the form of a complex number. Typically, this analog signal is amplified and shifted to the frequency carrier, for example Wi-Fi, in which the analog signal is shifted to 2.4 GHz in this example, and the signal is then delivered to the antenna. And the information carrying transmission signal is represented mathematically as the e power of I times frequency carrier times t. The signal is represented in mathematical form at the receiver as the yt equals the ht, and which is the channel convolved as the e power of I times fc times t, and the channel is crucial in wireless communication because it affects every received signal. As a result, it is critical to understand the channel characteristics. The propagation characteristics of a signal is an important aspect to understand while transmitting it from the transmitter to the receiver. There are various propagation characteristics to consider. Let's have a look at this image down below. As the receiver, an antenna transmitter PT will provide the signal to the vehicle or the PR, and the path loss is the initial propagation characteristics. The route loss is depicted in this image by blue lines. It denotes a direct and straightforward approach to the recipient. And we characterize propagation by calculating the ratio of received to sent signal across the distance. The route loss is shown by the blue line in the graph, and the blue line shows that there is a very gradual shift in this ratio. Shadowing is the second propagation feature. Obstructions from an item cause shadowing, and the item is represented by the red block or wall in this case, and the item has an effect on the signal because it exhibits small variations that deviate from the blue line. The multipath fading is the third propagation feature. The signal that reaches the receiver through several paths or reflections is referred to as the multipath fading, and the green line in the graph shows multipath fading. It demonstrates that the blue of variation occur more frequently than the red ones, and the ratio is not dropping in a regular manner. Path loss models come in a variety of flavors, I shall say. The first are Maxwell equation, the second are free space and two path models, and the third one is the ray tracing models. The fourth are the single slope path loss exponent models, and the final are the measurement based and standard models. Signals are made up of electromagnetic waves. Maxwell's equation, the first path loss model, explains the interaction between the electric and the magnetic fields, which are combined to electromagnetic propagation. It is, however, extremely complicated and unworkable. As a result, there are modeling approaches that are simpler to employ, such as a free space and two-path models. So, free space or loss model, line of sight. It is shown below in the picture. As you can see, the loss refers to the signal's ability to travel without encountering any obstacle on its way to the receiver. In general, the free space models say that the power declines are proportional to the inverse of distance squared. It is proportional to the lambda wavelength squared and inversely proportional to the frequency squared due to the antenna's effective aperture. Next up is the two-ray model. So there are two different ray models. The receiver in the two-ray model receives two sources of signals, loss and non-loss signals, and the non-loss signal was caused by reflections and refractions, and the power falls in this model is proportional to the distance squared. And when the distance is more than the threshold distance, the power falls substantially, and it is also says that it is not affected by wavelength or frequency. And the following model is general ray tracing. It makes use of the phenomena of reflection, scattering, and diffractions. And the red lines in this image are reflections, and the blue lines are scattering, and the green lines are diffractions. Because of the numerous reflections or refractions, the receiver may get a large number of signals. This model necessitates the use of site geometry and dielectric characteristics. The following model is a simple route loss model. It is a simplified version of the path loss model. When the path loss is dominated by reflection from objects, this model is employed. This is the equation that may be used to simulate signal transmission. The gamma or path loss exponent parameter is utilized in this model. The gamma should be between 2 and 8. And the R in this equation is for the location of the receiver, and the D is the reference point to the receiver location, and PR is the power received, and the PT is the power transmitted. And next is millimeter wave. So what's the big deal here? So millimeter wave, which stands for MM wave stands for millimeter wave, is a spectrum or frequency band that ranges from 30 to 300 gigahertz. This is due to the wavelength of electromagnetic wave being in the millimeter range at this frequency, and the millimeter wave frequency range is in the high spectrum bandwidth. And the image above progresses from the lowest frequency spectrum in the top left and to the highest frequency spectrum in the bottom right. The 5G is allocated in the 38 gigahertz band in the United States. Now, the graph below depicts the power attenuation, which is shown on the y-axis, and the more the power attenuation, the worse it becomes. And the frequency is represented on the x-axis. According to the picture, the attenuation at 6 GHz is very high owing to oxygen absorption, and when there's a water, it has spikes in other situations. So, how can we overcome the difficulties I outlined earlier? So, the solution is that an empirical model that may be used to address the problem. The present channel modeling cannot be utilized in areas that are not suited for millimeter wave, and the initial cellular empirical models are based on considerable measurement, and the Okumura, Hada, and COS231 model, multi-slope model, and Wolffish-Albertoni model, and other are examples. And the empirical model, on the other hand, is location dependent. For example, the Okumura model, which was carried on in Japan, where there are several impediments. So that is it for today's video. I hope you can learn something from my explanation. I am very sorry if there's a confusion in my explanation, and I will see you on the next one. Thank you.